Hello and welcome back to Deeksha Karnataka YouTube channel, and today in the Masterstroke series I am going to discuss a very important chapter for all the KCET aspirants, that is current electricity. And if you are aware that almost 6 to 7 questions, up to 7 questions can come from this chapter, so this is a super important chapter. Even though the chapter length is not big, concepts are very concise, so we will not waste any time in this chapter. And if you are watching our Masterstroke series or in our channel, if you are new to our channel, definitely subscribe to our channel, join our WhatsApp group link is given in the description, so that you get all the new updates whenever we are posting a video. That update is getting posted in our WhatsApp group, so you don't miss out on any of the notification, right? So without much delay, let's start with the lecture. First, let us look into all the important concepts from this chapter. If you don't have time and if you want to revise quickly, what are all the topics that you should revise from this chapter? First of all, electric current. Definitely it is about electric current, so you have to look into that. Next is Ohm's law, another important concept. Then we have resistance and the relationship with resistivity, so that formula, also based on that formula a lot of question comes. Next we have drift velocity, very important concept. Drift velocity, mobility, electric field, etc. They are also linked with drift velocity, so they are also all important. A combination of cells can be combination of cells in series, combination of cells in parallel. Next we have KCL and KVL along with Wheatstone bridge. Wheatstone bridge is obviously part of KCL and KVL because we are applying KCL and KVL to calculate it, so I have not directly included Wheatstone bridge, but you can, if you study KCL and KVL, you can, and if you know the basic principle of Wheatstone bridge, you can answer all the questions related to it, right? Now let's start with the first topic of today, that is current electricity or electric current. The net amount of charge Q is flowing across the area of a forward direction in the time interval t, then the current is basically given by Q is equal to I is equal to Q by T. Here you have to remember that I is basically considered to be a fundamental quantity, even though it is appearing to be relation with charge and time, but I is considered to be a fundamental quantity, so its dimension is generally denoted by symbol A. Okay, that comes from the fact that its unit is ampere, right? Currents are not always steady, and hence more generally we define the current as follows. So in terms of if the charge is varying with time, then current can be defined by dq by dt. This is a interesting formula. In some cases they might give you a time variant charge and they might ask you to find the current, so in that case you have to use the differentiation to find the current. So just to give you a reminder that current not always q by t, you sometimes have to do the differentiation as well, right? Now let's move on to the electric currents in conductors. So especially for conductors, electric charges experiences a force in the presence of external electric field. So when current is being carried through a conductor, the conductor experiences a force. Okay, now electrons being negatively charged move opposite to the direction of electric force. Suppose I have a conductor and I have some electric field applied. Okay, I have applied some electric field across the conductor. In that case, the electrons present in the conductor, we know the conductor is made up of a lot of free electrons, we have discussed in our previous chapter, right? Now here the electrons move in the opposite direction of the applied electric field. Very important concept to know that electrons always move in the opposite direction of the applied electric field. Okay, and only electrons can move, protons cannot move. Okay, metals having a large number of free electrons, these free electrons accelerate in the presence of external electric field. Obviously it experiences a force. So suppose this is an electron. What is the force acting on it? The force acting on it is given by Q into E, that is E into electric field, right? And then it starts to accelerate. What is the acceleration? Acceleration is basically force divided by mass of the electron. Okay, this is the acceleration, and this acceleration is acting on the electron whenever it is subjected to external electric field. Okay, this gives rise to the electric current. So electric current is basically when electron moves in the presence of electric field. That is the basic meaning of electric current. Okay, electric field is very, very essential for electric current. Okay, so first let us look into the Ohm's law. Ohm's law is if the temperature and other physical conditions remains the same. Very important line. So temperature and other physical constant, that means the physical state. Okay, it cannot change its state, right? It cannot become, so suppose I am passing a current through a metal, suddenly it melts and become a liquid, then obviously Ohm's law will not be applicable to it. So if temperature and other physical conditions remain same, then the current through the conductor is directly proportional to the applied potential difference. Very important and interesting formula. Obviously we know that V proportional to I, or V is given by V is equal to IR. R is called resistance. The constant of proportionality R is called the resistance of the conductor. The resistance R not only depends on the material of the conductor but also on the dimensions of the conductor. So it depends on the material. If you are using copper, or if you are using silver, or if you are using iron, and it also depends on how thick or thin the conductor is. Okay, now other form of Ohm's law, as I said that electric field is very, very important for Ohm's law, and that is why this is another form very, very important for Ohm's law. J is equal to sigma E. J is basically, J is current density. Now what is the meaning of current density? Just a second, I made a mistake in the spelling. Okay, so J is basically current divided by area. So this is the current density. J, its unit is ampere per meter square. Okay, so this is a just simple theory. Now let's move on to the resistance and resistivity. Okay, so resistance is basically proportional to the length of the conductor. Longer the wire, more will be the resistance. Now what is the resistance? Resistance is when it is getting stopped by other electrons. So some electrons wanted to move and some other electrons are not allowing it to move. So that is basically the resistance, and longer the length, obviously longer will be resistance. Next is resistance is inversely proportional to the area. So you can consider this to be a highway. Okay, the electrons are basically moving cars through the highway. Now wider the highway, okay, faster it can move. Now if the narrower is the highway, everyone is passing. Now highway is narrow, there is a big truck sitting in the middle, he is moving slowly, so all the cars behind the truck will also move slowly. So if the road is longer and narrow, then definitely resistance will be more, but if the road is wider and short, electrons can quickly move from one point to another point and resistance will be less. And if you combine these two equations, you get R is equal to rho L by A. Here rho is called the resistivity of the conductor. Okay, and this depends on the material of the conductor. Okay, resistivity is independent of the geometry of other material. It varies from material to material and only on the temperature. So obviously resistivity varies from material to material, but it is independent of L and A. Okay, now temperature dependence of resistivity is given by rho T equals to rho naught 1 plus alpha T minus T naught. T naught is basically the starting temperature, okay, and T is the final temperature, and as you increase the temperature, as you can see that the resistivity increases. If you decrease the temperature, resistivity decreases. This is for normal conductors. Okay, semiconductors, they obey different law, but for normal conductor this is the formula, and here alpha is called the coefficient of resistivity. Coefficient of resistivity. Now if everything is constant, resistance also follows the same formula. RT equals to R naught 1 plus alpha delta T. Same formula, same alpha. Okay, only thing is that resistance can change with the length and area, but if length and area is constant, then resistance also obeys the same formula. That's it. Now let's move on to the next part, drift velocity. So drift velocity is basically defined by this term. Okay, Vd is equal to minus electron into electric field divided by mass, that is the acceleration. I told you acceleration, what was the acceleration? Acceleration was given by EE divided by M E, right? That was the acceleration. Now if you multiply it with the time constant, that is the time taken between two collisions of the electron, okay, then you get the drift velocity. Now why it is negative? Drift velocity is negative because electrons are moving in the opposite direction of the applied electric field. That's why it is negative. Okay, everything explained. Now let's move on to the current part. So sorry, there was some error in here, so drift velocity level came later. So drift velocity is given by Vd is equal to E by m into delta t. In case you forget, you have to remember this is acceleration, this is the time constant. Okay, now relationship between current and drift velocity, very common equation. I is equal to NEA Vd. Here n is basically number density. N is the number density, that is the number of electrons per unit volume. Okay, number of electrons per unit volume is called number density. E is area, E is charge of an electron, A is area, Vd is drift velocity. Next is mobility. Mobility is defined by Vd by E, that is drift velocity per unit electric field, how quickly an electron is moving. Based on that, this is called mobility. So this is also an important equation. I have seen some objective questions where they have asked which of the following is wrong, and in this case they have used the definition of mobility. So be careful, also stay aware of this equation as well. Okay, from here also you can find mobility, that will be you can ignore the negative sign for sake of only the magnitude. So drift velocity mobility is given by E tau by m, right? You divide Vd by E, so you get, this is the another equation for mobility. Okay, now if you are preparing for PU board, there are a lot of derivations involved, but we are not going into the derivation part here. Okay, this is for KCET. Formulas are important, concepts are important, and practice is important. So limitations of Ohm's law, what are the limitations? Obviously V ceases to be proportional to I. That means if you plot the V versus I, normally one more thing I forgot to tell you, that for any normal conductor, V versus I graph is always a straight line passing through the origin. Okay, V versus I graph is always the straight line passing through the origin. That dotted line here is the perfect conductor. Okay, but if you keep on increasing the voltage, after some time, some conductors generally do not follow this proportionality dotted line, but they tend to deviate from it. So this is the case where it says that V cease to be proportional to I. Okay, I and V are no longer proportional, they changed their relationship, and it is complicated right now. Right, so let's move on to the next question. The relationship between V and I depends on the sign of V. So this is another example. This is the graph for which, please mention that in the comment below. I am not going to tell you here. We will discuss about this chapter in future, but what is this graph shows that as the V is positive, the graph is something different, and as the V is negative, it is completely giving you a different value. So that is the second case where current actually depends on the sign of V. So positive, there is one response, negative voltage, another response. In general, for a normal ohmic graph, it is not so. It will be still, suppose in this case, suppose I have a graph like this. So V is proportional to I means normally we represent this, right? Now what will happen if I make the V, if I change, me, I means me. Okay, don't get confused with the current. Okay, so if I change the current direction, voltage direction to the opposite, then it will also be a straight line, and it will be a continuous straight line. It does not depend on the sign of the V. The same line will be extended to the negative side as well. But in case of this particular device, okay, the it behaves something in the positive V, something in the negative V. What is the name of this? What is the name of this? What is the name of this? Mention in the comment. Okay, now next is the relationship between V and I is not unique. That is, there is more than one value of V for the same current I. Okay, so this is a case where you get two values of V, that is it is not single. Okay, so V and I are not unique. So for in this case, if you see, for each value of V you are getting unique value of I, or if you say that for each value of I you are getting unique value of V. But in this case, if you consider voltage is changing, and if you plot this graph, you see that for a single I you are getting two different V's. So two different V can give you same I. Okay, and only except one point. Other than that, even though initially it looks like that it is obeying Ohm's law, slight deviation, but as you go progress further into the voltage, and you are saying that there is a peak here, it is like coming like this. Okay, so this is a non-linear resistance region. The resistance does not linear. Now if up to this point, if you see up to this point almost, okay, it is obeying Ohm's law. So you might think, okay, this is an ohmic conductor. You draw up to this point and you stopped. You said, okay, maybe it is an ohmic conductor. But if you continue further, then you will see that it is not an ohmic conductor. An ohmic conductor is actually ended here. After that, it is no longer an ohmic conductor. So these are the main three limitations of Ohm's law. So Ohm's law is unlike Newton's laws of motion or conservation of energy. It is not an universal law. There are a lot of things which does not obey Ohm's law. Okay, there are good reasons for that as well. But in a short region, short voltage and short current, generally short means small range of the voltage, generally it obeys Ohm's law for some period of time. Okay. Now combination of resistances. So series combination, obviously we know that I am not wasting too much time. You just need to remember just the values that series combination, when resistances are connected in series, you get R equivalent is basically sum of all the resistances, and in parallel combination it is 1 by R eq is equal to 1 by R1 plus 1 by R2 plus dot dot dot. Now remember that if there are only two resistances are there, then you can simply write the R equivalent. Just to remind you, I know most of you already know this if you are following my lectures from the beginning. Okay, this is R1 R2 plus divided by R1 plus R2. This is the formula for equivalent resistance. Now one more thing to remember, that in case you are solving this for more than two resistances, this is actually, after calculating this, you have to take the reciprocal of that value. Okay, I have seen some student said R equivalent is equals to, they have calculated 3 by 5, so the equivalent resistance is 3 by 5. Okay, don't make this mistake. Okay, so you have to be careful. This will not be the case. The R equivalent will be 5 by 3. So R equivalent will be, you have to take the reciprocal of the right hand side. So this is the answer, because it is 1 by R eq, right? So you have to be careful, don't make such mistakes. Next is electrical energy and power. Let's look into that. Current, a cell of voltage say V is supplying power to a resistance R. Then what is the power consumed? First, energy is given by VIT, vitamin. I like to remember this way. If you are someone who still remembers old Joule's law of heating, then I square RT is the other formula. But I like to say energy is vitamin, vitamin is energy. So energy is basically given by vitamin. Or the other formula is I square R into T, or sometimes it is also written as V square by R into T. These are the three forms of energy. Now power is basically given by, in the same way, if you divide the energy with time, you get the power. So first it is Vodafone Idea by, okay, then next is I square R, and last is V square by R. So these are the equations for power. Sometimes based on the question and based on whatever values are given to you, you have to choose different equations. Okay, for example, there is a question where V and R is given. Okay, a 220 volt bulb, a 220 watt bulb is connected to across a 220 volt supply, calculate current, etc. So in that case, voltage is given, power is given. You have to calculate the resistance first. Okay, or maybe if you use this formula directly, you can calculate the current directly. So based on what question is asked, what you need to find, you can use any of these equations directly to save some time. That's it. Now next part is So where do we use this transmission of power? So power, when it is transmitted, the transmitted power formula is given by P square into RC by V square. So higher the voltage, okay, less power is consumed. This power, the supplied power, is actually constant. RC, you cannot reduce it below certain value, but what you can do is that you can increase the voltage so that the power which is lost in transmission, when the power line is getting it is transmitted from the power station to your home, if you can somehow increase the voltage, then the loss of power is very, very low, because we know that when the there is a current flowing through a conductor, it gives rise to the heating effect, Joule's heating effect, and we lose a lot of energy. So from the power source, power station where it is generated, maybe a hydroelectric power station, maybe a coal power station, maybe a nuclear power station, or a wind turbine, whatever it is, from wherever you are getting the power at your home, maybe a solar power station, okay, unless it is fitted in top of your building, okay, if it is coming from somewhere, always remember that when the power is coming, there is a tendency that it loses power because of the heating, okay. Only way to reduce that is by increasing the voltage and reducing the current. Okay, power rating of a bulb. So in some cases power rating of the bulb is given and you need to calculate the resistance. So this is the direct formula to calculate the resistance of the bulb, okay. And current is again P is equal to VI. So in that case current can also be calculated P by V, okay. So based on the problem, based on the questions, we will solve some questions in our question answer sessions next. There we will solve some questions based on bulbs, and all these concepts will come here, okay. Now let's move on to the electric cells combination. So we have two combination of cells like resistors. First is cells in series and cells in parallel. So cells in series basically is simple. You add all the EMFs, you add all the internal resistances, you get cells in series. Now what is the cell? Cell is basically not an ideal battery, but it is a part of a battery having some internal resistances, okay. So like the small battery that you use in your remote controls, or in your there is a battery in your mobile phone as well. They all have they are basically sum of tiny cells, right? So all of them are basically consisting of small cells, and each cell has their own EMF power source, and they also have some own internal resistance as well, right? They are the internal resistances are basically fixed for a cell. Now cells in parallel, when the cells are connected in parallel, the equivalent EMF is given by epsilon 1 by R1 plus epsilon 2 by R2 plus epsilon 3 by R3, okay. And here the equivalent resistance is basically like the all the resistances are connected in parallel. So if you connect cells in parallel, so this will be the case, cells in parallel, and this is the cells in series, okay. Now current in both cases is basically given by R equivalent divided by resistance plus R equivalent, okay. Now this can be sometimes written as sum of epsilon I by Ri divided by 1 by R equivalent. This is also sometimes another form of cells in series, cells in parallel, right? Now let's look into the Kirchhoff's rules. Very important part, that there are two rules. Junction rule, sometimes it is called junction rule, sometimes it is called Kirchhoff's current law. At any junction, the sum of the currents entering the junction is equal to the sum of the currents leaving the junction, okay. So basically we have a junction. Junction means where more than one points are meeting, right? Bangalore junction, right? So there are a lot of junctions. Delhi junction. So where multiple lines meet at a point, they are called junction, okay. So junction is basically, now suppose I have three resistors like this, so I1, I2 and I3 are entering the junction, Okay, this is the junction where all of them are meeting, and at the same time, say I4, I5 and I6 are exiting the junction. According to Kirchhoff's junction rule, all the currents who came there, that should be equals to all the current that exited. Individually they may not be same, and most likely they are not same. Okay, but okay, so 1 2 3 6 5 4, right? Good way to remember. Anyway, just to joke apart, so you have to remember that whatever current they are coming in, the total sum of all the currents, that should be equals to total sum of all the currents exiting. In some cases, current is coming through 2 paths, but current is exiting through 3 paths or 4 paths. And in some cases also, current is coming through 1 path, it is exiting through 2 or more than 2 paths. And similarly, current is coming through 5 paths, 5 different paths, but exit way is only 1. So you have to adjust accordingly and solve based on the need of the question. This is a direct consequence of conservation of charges principle. Okay, so this is a consequence of the conservation of charge principle. So Kirchhoff's current law is basically saying that charge entering the junction, the same number of charge should exit the junction per unit time. Now what is charge per unit time? Charge per unit time is current. So current entering the junction should be equals to current exiting the junction. As simple as that. Now next is loop rule, also called Kirchhoff's voltage law. Okay, Kirchhoff's voltage law is more common KVL. Okay, but in your NCERT textbook it is mentioned loop rule. If you see the loop rule question in the exam, what is loop rule, etc. So don't get confused. Loop rule is basically Kirchhoff's voltage law. The algebraic sum of charges changes in the potential around any closed loop involving resistors and cells in the loop is 0. Now while writing we will write it like that, but while solving questions what we have to remember is that suppose we have a cell and we have a resistance, we have some cells, some resistance, there are some other parts also. Suppose we have some other resistance, some other cell. Okay, there may be multiple. This is the simplest circuit. Okay, so say this is R1, this is R2, this is R3. Okay, this is say V1 and this is V2, this is R, say 4. Now if we see such kind of things, you have to remember that you have to, first of all, you have to assume the direction of current in each branches. So see, suppose I current is coming over here, I1 say. Okay, then there is no other path, so I1 current must exit from the battery. Okay, this is clear. Now whatever current is exiting the battery, the same amount of current should enter the battery back as well. Okay, in some cases some batteries are connected such that instead of supplying the potential to the circuit, it can be reversed as well. That is not our KCET level questions, that might come in your JEE mains and JEE advanced level question. Okay, so we have to remember that whenever we assume the direction of current, it may be correct, it may not be correct based on the circuit, based on the parameters given in the question. Okay, so first of all you have to understand that whenever first starting point of our journey should be from the battery. That is easier to remember. Okay, so we will start from the battery and we will move in a loop, and we will end back at the same battery from where we started. Okay, and while doing so, we will always try to choose only one battery at a time. If possible, no battery, that is better. Okay, now what is the voltage drop across this resistors? Voltage drop any resistor is basically I into R, Ohm's law. So voltage drop across this resistor is I1 R1, voltage drop across this resistor is R2 I2. And voltage drop across this resistor is basically, again this current will be I1. As I said, I1 current is exiting, I1 current should enter back, so this will be I1 R3. And if you add all of these voltages, then that should be equals to V1. So while writing we will write like that, but while doing numerical questions on our right hand side, we will use the battery's voltage, as long as the direction of the current is as the same as the direction of current that battery wants to pass through. Okay, so this is what you have to careful. And in case some cases, suppose there will be circuit diagram already given to you with arrows, and when you are considering a particular loop, if you are going along the direction of arrow, everything will be positive. But if you are going somehow, suppose that in the same circuit, okay, the direction for I2 is given, direction of I2 is given in the opposite direction. So in that case, when you apply the Kirchhoff's voltage law, you start here, you are going in the direction of current, but suddenly this is coming in the opposite direction. So what you have to do in that case, you have to say that I1 R1 minus I2 R2 plus I1 R3. So if you are going in the direction of current, then voltage drops will be positive. If you are following a path where you have to go through a junction where current is going in the opposite direction, then it will be a negative value. Be careful about this kind of short things. Okay, this law is based on the conservation of energy principle. So KVL or loop rule is based on energy principle, whereas junction rule or KCL is based on the conservation of charge principle. Now let's solve one question. Okay, each of the resistance in the given cubical network has a resistance of 1 ohm, equivalent resistance between A and B. So this is a typical question, common in KCET. It came at least twice in KCET. Value of the resistance has given different cases, different times, but let us understand this problem. So current, this current I is entering this loop, and if I current is entering, the same current will exit the circuit, right? Now if you see, if you start from here, what is the minimum path starting here to reach at this point? Okay, the minimum path you can take this 1, 2, 3, right? 3 resistors. Similarly, in this path also 1, 2, 3 resistors, all are equal. Again through this also 1, 2, 3 or 1, 2, 3. Okay, no matter how you go from here to here, the minimum possible path is always same. The minimum possible, it does not matter whether it is 3 or 4, the minimum possible path is always same for all the branches. How many branches are there? Number 1 branch, number 2 branch, number 3 branch. So all 3 branches are here equally treated. They all have equal holding, that I also have the minimum path, I also have the minimum path, I also have the minimum path. So basically that means that if the current I enters it, all of them will equally share the current amongst them. So what is the current through this resistor? Current through this resistor is I by 3, this also I by 3, and this also I by 3. Okay, now similarly, now after this current reaches here, okay, also one more thing, if I by 3, I by 3, I by 3 is exiting this, the same logic can be applied here as well, and you can say that I by 3, it is nothing about KCL, but this is just logic. So whatever current is exiting, similarly the current that is converging here will also have I by 3, I by 3. Now at this junction, this I by 3 current is again splitting into 2 equal paths. It can either go from here or it can go from here. Okay, so here this I by 3 is dividing into 2 halves. So current through this is I by 6. Similarly, current through this will be also I by 6. Again, you can apply the same logic here. I by 6. Okay, I by 6. Now, sir, why you are doing this? The I by 6, I by 6, I by 6, they are combining again. So you are getting the total current. Now what we will try to do, we will try to find the equivalent resistance. So equivalent resistance means no matter whatever is the case, the current should be remains the same, that is I current entering, I current exiting. Okay, and the voltage drop, if we can find the voltage drop, basically we can find the current in this case. Okay, now this circuit, assume that this entire circuit is connected across some battery. Say V. It is connected across some battery, say V. Okay, now equivalent circuit again. What did I say? The same battery will be there, same current will be there. So what will be the value of R equivalent? Value of R equivalent will be V by I, right? Value of R equivalent will be V by I. Now if somehow I am able to calculate V by I from one of the loops that I have drawn here, then I can find the equivalent resistance. As simple as that. So that is our target. Our target is to find one of the loops through, so that we can calculate the equivalent resistance. Now whatever loop we can consider, any one of the loop we will consider this loop. Suppose we are considering this loop. We will apply KVL in this particular loop. All the currents are going in the same direction along the battery, right? So what is the KVL says? KVL says that this current into this resistance say R. For now I am doing the general solution. The R value we will put at the end. R value can be anything. So this is R, this is R, this is also R. Okay, all the resistances are same. Now what is the voltage drop across this resistor? This resistor voltage drop is I by 3 into R plus. Why plus? Because we are moving in the same direction of the current. So in this case I by 6 into R. So I by 6 into R plus again R into I by 3. I by 3 into R. So we started here, we reached first resistor, we reached second resistor, we reached third resistor. Now we are out and we are back to the battery. So back to the battery means that should be equals to V. Okay, so now solve this. So I by 3 plus I by 3 is 2I by 3 plus I by 6 into R equals to V. You can solve it anyway, does not matter. So it is basically 6, and then we can say that 4I plus I, that is into R equals to V. Okay, so we can write this as 5I by 6R equals to V. Now what we are trying to find? We are trying to find V by I. So 5R by 6 equals to V by I. Okay, so this is basically, what is this? This is R equivalent. So R equivalent is basically 5 by 6R. This is the general solution. Now based on whatever value of R will be given to your exam, you can solve this. Now if there is a cubical structure like this, you can directly use this formula to find the R equivalent. Okay, you do not need to solve this long process. This is just for your understanding. In some case, some other question comes where you have to use your brain, where you have to use this analysis method. So this is a way. This is not only a solution, this equation itself is an equation that you have to remember. R equivalent is 5 by 6 R, right? The answer given here is incorrect. This will be 5 by 6 ohm. Okay, so don't worry about this answer given here. It will be 5 by 6 ohm. So here R is given as 1 ohm, so R equivalent will be basically equals to 5 by 6 ohm. Okay, now next question. Oh, sorry, my mistake. And this is not the case. They have given us an MCQ. I thought this is a long question. Okay, so this is given as an MCQ, so answer is basically 5 by 6 ohm. Obviously that's what we have solved it. So 5 by 6 ohm. Now let's move on to the next concept, that is Wheatstone bridge. Wheatstone bridge is the concept where we have 4 resistances, R1, R2, whatever way you can write. I like not like this. I have taken this diagram from your textbook. So P, Q, R, S. Generally this is the way I used to write, and the condition for balance is basically galvanometer, there is no current through the galvanometer, so Ig through the galvanometer should be 0. Okay, and in terms of resistances, it is R2 by R1 is equal to R4 by R3, or what I like to write is P by Q is basically equals to R by S. Okay, P by Q equals to R by S. Now there is a short question where they said that galvanometer and battery are inverted. Okay, so galvanometer is now connected across this and the battery is connected across these 2 points. What will happen to the equilibrium point? If the consider that there is a balanced Wheatstone bridge, and if you rotate or if you swap the galvanometer and the battery, nothing will happen. It will still remain in balanced condition. When no matter, even if you rotate the galvanometer, rotate the battery, this condition will still be satisfied in that new condition as well, and it will again remain balanced. Okay, now another question, this is based on Wheatstone bridge concept. Okay, so whenever you see this kind of structure, basically you remember that this is a Wheatstone bridge question. Okay, this is a Wheatstone bridge question, and this R is basically this is the R which is basically like the this R is basically the galvanometer. Okay, now you have to check that if this by this equals to this by this. Okay, so this by this, you can draw this like this way. Okay, if you wish to. Okay, but mostly I have seen in KCET exam they don't give any complicated circuit, they give you simple this format Wheatstone bridge where all the resistance are generally equal. In this case 2024 exam they have given you 2 combination of that. Previously they used to give 1 combination. Now don't get afraid, only thing you have to remember, because it's a Wheatstone bridge and because this by this equals to this by this, that means it is in balanced condition, you can simply ignore this resistance at all. You can ignore this resistance completely. Okay, so how to do that? We just simply erase this resistance. Okay, we just simply erase this resistance, nothing is there, then it will be easier for you to understand. Okay, I have the privilege of using white color, so I can erase it clearly, otherwise you have to erase it in your mind. Okay, so you can see that basically this means that these 2 resistances are connected in series, these 2 resistances are connected in series, and then they are connected in parallel. Now if you draw it like this becomes clear, right? So now again if you saw the other half of the circuit, again this can be deleted simply because this is also galvanometer, and in balanced condition no current is passing through the galvanometer, no current is passing through the galvanometer means you can simply remove that component. If there is no current passing through a component, then simply you can remove that component, right? As simple as that. So we just removed all the components which are creating damage in our calculation. Now you can simply use laws of the resistance, parallel and series combination. So R plus R is 2R. Okay, R plus R is 2R, this R plus R is again 2R. Now 2R in parallel, 2 equal resistances connected in parallel, then their equivalent resistance, say R1 in this case, will be 2R by 2. Okay, if n number of resistances, n number of equal resistances connected in parallel, their equivalent resistance is R by n. Okay, I forgot to give you the formula in our series and parallel cases. Okay, if n number of equal resistances connected in parallel, their equivalent resistance is R by n. Similarly, if n equal resistances are connected in series, their equivalent resistance is NR. This is a easier way to remember in case of, this occurs mostly in case of parallel, though series is obviously easier. So that is why even in exam also they don't give you based on series, they give mainly parallel. Okay, so it will be basically equals to R only. So the entire part of this entire resistance is basically R. Similarly, if you do the same thing on this case also, you will get 2R, right? So what is the total resistance? Total resistance is R plus 2R. So R plus 2R, that is total resistance is 3R. So entire this big looking, scary looking circuit, but if you break it down, you get 3R, and this can be done very quickly if you are familiar with this kind of questions. Now what is the current in the circuit? So current is basically V by equivalent resistance. So V by 3R, that is in this case V0. So V0 by 3R is the current in this circuit in this particular given case. So I hope this helps you and you enjoyed today's lecture, and if you have any doubts, any questions, anything else, please don't forget to mention in the comment below. I will be back with a live session in next week, and before that Monday also I will have a recorded video session for moving charges and magnetism. See you on Monday's class. Till then, bye.